Okay, checking time. 傅陆云，赵佳琪，
到，
崔家园，
到，
陆一凡，
到，
姚如歌，
到，
李宗浩，
到，
Ricky, Jarnat, Dean, Suna, 蔡家峰，Lexi, okay, first, we're going to take a short review on the introduction about the reflectivity and the transmittivity of the EM waves from surface between two mediums. So we have expressions for the average magnitudes of the power densities for the instant reflected and transmitted energy. So for the power density for the instant, we do not consider as polarizations because it works for the HOV pores. Okay, so it can be expressed as the electric field phasor square divided by 2 times its intrinsic impedance. All right, if it's in free space, then it's eta node. Or in lossless medium, it's eta node. And for loss medium, it becomes a complexity. All right, a complex number. So and this works for the reflected, the same thing. And for the transmitted also. Another medium may be medium 2. So that's this one. And if we want to take or we want to calculate the corresponding average powers carried by the beams. So for power, for the instant power, I do not consider this one. Okay, for the instant power, it can be calculated by the product of the instant power energy times for area integration. All right, for area integration. So if both along the same direction, so it's just the product of both scalar values, and for the reflected, same thing, and for the transmitted, must be something. Right. If there is if the surface, for example, is normal direction, there is angle between the normal direction and the power density. So it becomes under this area. For example, the beam width across the area is around 8, for example. So it becomes as I times A times cosine theta I, right? If it's theta or theta I or theta. And here is the same thing I'm neglected. So this is for the powers. And after that, we calculated how to conduct the reflectivity. All right. So the reflectivity can be expressed by gamma, and finally, H. Consider for the HOV pores can be calculated by the reflection coefficient HOV squared. All right. So this is for the reflectivity, and for the transmittivity, the reflection. It can be expressed as also the transmission coefficient, no matter h of equal times eta 1 cosine theta 2 divided by eta 2 cosine theta 1. Okay, and it has two mediums, the medium 1 and medium 2. Medium 1 is intrinsic impedance of eta 1, and medium 2 is intrinsic impedance is eta 2. Okay, so this is the expressions for this part. So after that, we introduced a little bit part about the antennas. All right. So for antennas, we just consider one parameter is the far field region. So for the far field region, we define the distance between the antenna and the observation point is larger than the square divided by lambda, right? And so here we define the P as the antenna as a linear dimension, right? And the lambda is the wavelength as well. So this is the far field regions, the definition for far field distance. So for the Hertz's dipole, right? We just take the Hertz's dipole as a specific antenna, so it can be expressed as a line diameters. Lines 90 is two sides, and there's current going inside. So, and its total length is L. So we take a Cartesian coordinate system for the analysis. X, this is X, this is Y, and theta is along this line. And also, we transfer it to the spherical coordinate system. We define the point Q here. So it's related to arc theta and phi, right? So this one, and here is theta, the zenith angle, and here is phi, the zenith angle, and also the radial coordinate axis r. So we can express, just let's assume there's current flow inside of this line, and this time varying current. So times sin omega t, sin cosine, that's not matter. Good. And also can be because it can be transferred to the exponential function j omega t, right? So this is the expressions for the current flowing inside, and we can get expressions for the we assume the eta is only along the electric field is only along the theta axis of the so it can be expressed as the electric field equals theta times phi j times the I node LK eta node times the propagation JKR, alright, for spherical waves, and since theta. So this is the electric field, and for the magnetic field, along the phi direction, right? So, and to each node divided by E of 1 theta, H this is the expressions for the electric field and the magnetic field. And they both propagate along the radial direction. So its vector k is unit vector along the radial direction. So until now, we just concentrated on the electric and magnetic field, and we also has the power densities expressions, right? So it is half, and the real part of the electric field cross product the magnetic field star, like this one, and its magnitude we get is related to the r theta, right? It's not. It's r theta, and it can be expressed as 32 pi square r square times eta node k square, and also I node square and L square, right? And theta square. So here is the average power density, and it can be expressed as initial point times sin theta squared. So since S node is represented as the other part, right, on this part, k square, I node square, L square divided by 32 pi square, capital R square. So this one is expressed by this component. And we also conducted a normalized radiation intensity. Normalized radiation intensity F. Alright, and it can also be represented as F equals the power density divided by the maximum part. Right? So, and this value is dimensionless. So, and this parameter or the power density can only be used to represent the antenna pattern, right? So, when we wanted to take measurements, we already transfer it to the normalized radiation intensity. And from here we can see that because the F, the normalized radiation intensity F parameter, it only depends on angles, right? As when we create the data sheets, for example, for the antennas, it only depends on the theta of and phi, right? These two parameters. And the S max is also, for example, the S max means what? The S max means, from this equation, means theta equals to pi over 2, alright? When theta equals pi over 2, sin theta squared is maximum, it's a unit. So it becomes S max, and S max equals S node also. So from that one, we note that the F theta phi it equals sin theta squared, right? So that means the radiation pattern for a person dipole antenna can be expressed by a simple function or a simple line, which is sin theta squared. So this is the antenna pattern, and as we mentioned, Monday, it's shaped like it's for the elevation pattern. It's like this one, right? So this side also the same thing. And from the Venus pattern, it's like a Dunkin' Donuts shaped. So this is the patterns, and if we want to, this is just for the Hertz's dipole antenna, and if we wanted to transfer it to much more popular antennas, that's what we use right now, it's like the Hall antennas or the dish antennas. So we're gonna have much common expressions for the analysis or for the antenna characterizations. So an antenna pattern is usually used to describe the far field direction. It's really used to describe the far field. Directional properties. So for the among it, we also introduced a principle, all right? It's like a reciprocity. Right? For the reciprocity, that means if the antennas at the transmitter side and the receiver side are identical, then we would consider that both have the same patterns, right? The antenna patterns. So this is the reciprocity, which gives us the method to just consider each one of them, even though they are at the transmitter side or at the receiver side. And for the channel analysis or calculations, we can just consider it maybe at the transmitter side and the gain or the pattern of that. Then we can also just put them identical at the receiver side also. So, in generally, the antenna pattern, or we can also call it radiation pattern, is a three-dimensional, right? It's a three-dimensional plot. And it displays the strength of the radiated field or the power density as a function of the direction. So it looks like this one. So it's three-dimensional, and for the if it is along the zenith angle, and alright. So from this range to this range, we can take a plot like this one, and usually we just take the for the zenith angle equals pi over 2, 90 degree, right? It's along this line. And we also take the zenith angle is equals 0, it's along this line. Usually we have this the plots in these two planes, right? It's like this one. So we put curves actually like this one or like this one. Alright. So let's continue. If we wanted to consider if we have power density and we have area, as we mentioned previously, we can calculate the power calculated by this equation, right? It can be expressed as dot product A, right? So this one. So here we consider the at far fields, directly the spherical waves. If our aperture of the antenna at the receiver side is very small, and it satisfies the far field conditions, then we can assume as plane wave, right? So if But if we consider it as a spherical beam again, so and in the spherical coordinate system, so we set here as first we set here as Cartesian coordinate system. This one x, y, theta, and we take the origin as this. We take the center of the sphere as the origin of the coordinate system, and then we can get change the color. Such part of the sphere. Okay. Part of the sphere. Okay, part of the sphere, and we just take an area unit on it. So, for example, we set it this area, small area or H, this area. So this area, which can be expressed, I think most of you should be familiar about it, is can be expressed. So the A can be expressed as the R square C theta, right? And the d theta defined for the unit area on a sphere in the spherical coordinate system. It can be expressed by this equation, right? So now, if we know and its direction, for its direction is along the radial direction, right? This direction. So its direction is just the normal direction of the sphere. This unit area. Now, if we know, for example, for the isotropic source. For an isotropic source, that means this is just a point source maybe, and over the whole surface of the sphere, its coordinates is uniform, right? It's uniformly distributed, and we can calculate the power radiated from the source and crossed through or passed through this unit area. So it can be expressed as the density times the unit area, right? So here, because it's along this radial direction, and the power density also follows the same direction, so we can just express by the scalar. So it can be expressed by this one, which means the calculation is simplified. All right. So here for the unit area, the dA. It can also be simplified further. So for the for a planar surface, we has a planar angle to represent that. All right, and for the spherical or for the in 3 dimensionals, we also use a solid angle, right, to represent the angles. Solid angle. For solid angle, we usually use omega to represent that. We do not use theta or not use phi. All right. So for this part, for the dA, it's related to a solid angle d omega. It can be expressed as the area of this corresponding to the solid angle divided by its radius, square of its radius, right? So it can be expressed as sin theta, d theta, phi. So this is a solid angle which related to the planar angle, right? An angle is just like theta or phi for these situations. So that means the expressions for this question can be expressed as r squared s times d omega. All right. So the expressions for the power positive the row, the assuming area can be expressed by this way. So if we look at for a whole sphere, that means the integration of dA equals 4 pi r squared. All right, the area of a sphere. That's why this one. So that means for the whole sphere, its solid angle equals 4 pi. All right. So now, if we want to take this one further for much more general situations. So for much more general situations, which means the power density cannot be uniform, right? If our source is not just an isotropic source, so the power density becomes axis dependent, right? It depends on the radius, depends on the zenith angle, depends on the azimuth angle also. So it cannot be uniform. That means when we wanted to take the or obtain the power patterns for the whole area, we need to take it as the power equals r squared times s theta phi times d omega, right? Sin theta, d theta, d phi. So this is a general expression for the total power radiated by the antenna, right? So when we wanted to take integration of that, so it becomes integration of theta and phi, right? So for theta, it changes from from 0 to pi, all right? And for phi, it changes from over a circle, right? It changes from 0 to pi. So this is and becomes an integration for that one. And also, as we mentioned previously, the what? The S, the power density can also be expressed as the maximum of that one times the normalized intensity, right? And the times sin theta, d theta, d phi. And as we mentioned previously, this factor, f factor, does not depend on the radial component or the axis, right? So it is only depends on theta and phi. So this one. So And this S max is constant, so it can be modeled out of this integration vector. So it becomes like this one. And so until now, the total output, the total outputted power can be calculated by this equation. So if we know the normalized power intensity F factor, we can take an integration based on this equation and get the total output power or the total radiated power. So this is the total radiated power from an antenna. Expressions. Okay. Now we wanted to obtain the antenna pattern. So let's come back to this plot. You see, here is the F vector, or the normalized radiation intensity, which depends on theta and depends on phi. So from this one, for simulation, it's convenient for us to get a three-dimensional plot, right, like this one. But for measurements such like using the vector and network analyzers, and because we need to consider the time for the measurement, right? So we just take the, for example, the zenith angle theta, of course 90 degrees. Then we take the plot on this line, and we can get expressions. All right. We can also set the zenith angle phi equals 0 also. So it's along this line. So this surface, this plane. The distribution on this plane. So we can get the expressions like, for example, if we express it in the polar diagram, so it can be expressed like this one, all right? So it has the this for phi equals 0. We set it as the main lobe, right? This is the main lobe, and there are also side lobes. The first, the second or third beam, and also we can get the back lobes, right? So this is in the polar diagram, and it can also be plotted in the Cartesian coordinate system. Also, it can be expressed, for example, in the a rectangular plot. Can be extended like this one. So from -50 to 50, we can just choose this part. Why we wanted to set it like this one? Because it's more convenient for us to obtain other factors or parameters. For example, the beam width and the non-beam width. All right. So it's more convenient for us for the analysis. But actually, both plots are always equivalent, always reversed, or reciprocal with each other. So there are, if we look at the unit of these lines, we can see that they use the decibel scale, right? We cannot use the linear scale, the decibel scale. So that means the F factor really should be expressed as the linear scale. So you transfer it to this one. And so this format is because this format is much more convenient for us to look at or to find the directional distribution of the radiation loads. It's more convenient to pick up that one. So these are the antenna patterns for the look here, just for antenna, and so here from this plot we can also see that we can find or we can measure or take measurements on the several kinds of loads, right? So the loads, or actually if we just take the main load for consideration, so we really need to know as the big dimensions. Big dimensions. So previously we introduced that if this one, we take a solid angle to represent the angle corresponding to the small area, alright? This one. So the solid angle should also be used for the beam dimensions analysis. So when we take an actual beam pattern, for example, it has a much obvious main load, right? Like this one, and it has many side loads and back loads, like this one. So it's corresponding to, if in a sphere, it would correspond to a solid angle, right? So the solid angle coordinate as and but when we want to transfer it to a sphere, a part of a sphere, it can be like sphere like this one, right? Like this one. This one. And the corresponding here is the corresponding solid angle, omega p, and this corresponds to the pattern solid angle. Pattern solid angle. So this is an equivalent solid angle, and so then what we can do to calculate that part. Previously, we calculated as an integration, right? The omega with respect to theta and phi, right? But here for the pattern solid angle, we need to multiply the normalized radiation intensity like this one. So for this one, and for the isotropic antenna, this half theta phi is already regarded as 1. So that means it converts it to the much formally of general distributions. But if it's directional antenna, then f theta phi has its own distributions, and then the pattern solid angle should be expressed by this equation, this one. And so this is the beam pattern. Then we have we also need to know the beam width. All right. For the beam width, what we really used is the half power beam width. We used what we used commonly used is half power beam width. So that means the half power means the power reduced to half of that, right? So when we come back to this plot, you see in the decibel scale, half power half means when it reduced to half means its power reduced to there's 3 dB. All right, reduced 3 dB. So that means from normalized, so the maximum should be 0 and comes to minus 3 dB. So we can get here the corresponding on both sides is theta 1 and theta 2. And then we can express the beam width beta equals theta 2 minus theta 1. Get the half power beam width. So for width corresponding to what? Becomes h, for example, h theta 1 or equals 1/2 and theta 2 equals 1/2 also. So at this point. And so here we choose maybe the phi equals 0, so it doesn't matter. So we can get the beam width on that half power beam width. Or we can also call it half power beam width of 3 dB beam width. So for this, we can also another parameter is the null beam width. Null beam width. Null means from this word, which means 0, right? It means the power reduced to 0. So when we look at the plot, this one, at this point, and at this point it's almost 0, right? It's reduced quickly. And if we take the angle unit to much smaller, and maybe this one line becomes a line of this one also. So this is the null width, which means the total width of the main lobe, right? So it can be also usually be read from the pattern plot or the diagram, especially in the Cartesian coordinate system, and it's more uniform and commonly used. So we get we can get the solid independent solid angle and the beam width. We would also want to know for antenna one parameter that we need to consider. Usually, our bit is really very important. Is the what? Antenna direct directivity. All right. So the antenna directivity, which related to the gain of antenna also. All right. So first, we need to consider as antenna directivity means it is angle dependent. All right. It shows along. It varies along the zenith angle, and it also varies along the elevation angle or zenith angle. And so now here Because first we consider is the peak directivity. So let's take a short review, take a short break, and then we're gonna come back. Okay, let's continue that part. So the peak directivity is defined as, use capital D represented, and defined as, should consider the normalized radiation intensity, right? So that means the peak directivity means the maximum of the normalized radiation intensity divided by average of that. So the maximum, because it is normalized, right? So its maximum should be, of course, 1. And the average means the take integration over the whole solid angle and divided by solid angle, right? So 1/4. And this one, here can be expressed as angle P, all right? The pattern solid angle. So from this one, we can see that for the pattern solid angle is reduced related to the peak directivity going to be increased, right? So, yeah, inversely, it varies inversely with respect to it. And also, if for an isotropic antenna, its pattern solid angle equals how much? Should be how much? Isotropic antenna, for example, by a dot source becomes a point source or pi, right? So that means its directivity or peak directivity equals 1, right? So that means when we consider the antenna gains or the directivities, it's not what? It's only a relative value, right? It's relative to the isotropic antenna, right? So it's not an absolute value. It's just a relative, right? So this one is called the isotropic. This one. So this is the this expression. And if we consider the this parameter again, it can be expressed as the maximum divided by the average, right? So it can also be represented as the maximum power, which represented the power density max times 4 pi r square, right? Divided by the radiated power. Like this one. And this one is related to the average, right? Times 4 pi. Take it into the uniform or the isotropic antenna as the it varies or it's distributed uniformly across the whole sphere surfaces, and so it can be expressed as the power density divided by the average power density also, like this one. So this, which means this one can also be expressed this term. Can be expressed as the radiation divided by 4 pi r square. It's equivalent to such expressions. This one, and And so this is the average value of the radiated power density, and it can be expressed by this one. So it can also be expressed as so, alright, isotropic antenna correlated to an isotropic antenna. So, which means the peak directivity can be expressed as the ratio of the maximum power density, this one, divided by the power density for an isotropic antenna, right? So when we want to define the antenna gain or the directivity of the antennas, we just take the isotropic antenna as reference for the expressions or for this one, because for the isotropic antennas, its directivity of course 1, so it's related to or it's relative to the unit 1. So it can also be defined in decibel, right? For the directivity, it's very defined decibel, 10 times 10 dB, right? dB, like this one. So for actual analysis, for example, we have a horn antenna, and we know, for example, the rectangular horn antenna. It looks like a guy. Okay, so as it has the beamwidth along this direction, all right, and along this direction. Along this direction and along this direction has two kinds of beamwidth. So if we take it as the this is what this is x, and okay, just to take the aperture for example. This one. So this is the beamwidth along this direction and along this direction. So this is x and this is y. So and intercept is this direction is theta. So this beamwidth is two-dimensional, right? And first dimensional is in the x o theta plane. Its beamwidth is x theta, and in the y o theta plane, its beamwidth is y beta. Right. So this is the half power, as we mentioned previously, or 3 dB beamwidth. Right. So we can simplify the solid angle, the solid radiation angle. Previously, we said if we want to get these values, we need to take an integration over the whole beam, right? Take an integration about that one. Here, if we note the half power beamwidth at both dimensions, and we can get it just like the multiplication of these two beamwidth differentials. So this one. So that means when we come back to the expression, for the directivity. Comes this part. I lost this part. So this is 4 pi. that one. So this expression. So omega p can be represented by these two parameters. That means the peak directivity can be expressed as 4 pi divided by beta, 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 beta. So this is for the simplification of to obtain the directivity. Now, if you have a beam and you know it's beam width, and you can roughly get the directivity of that beam, the peak directivity actually. So, if this is just for antenna, right? Because its aperture or its beam width is convenient. It's convenient structure that really we can get with a 1080 from a data sheet sometimes. And for horsing of dipole antenna, dipole antenna. As we previously know that its radiation intensity normalized radiation intensity times sin theta square, right? So we can get directly from the calculations. It becomes 4 pi over omega p, right? Omega p equals 4 pi f theta phi. Sin theta square is theta phi, right? The integration of that one. And finally, it can be calculated as 4 pi over e pi divided by 3, and it equals 1.5. D equals 1.5. This is in linear scale. If in the decimal scale, it equals 1.76 dB. So this is its directivity. So we can see that for a Hertzian dipole antenna, it also has a peak directivity, which is not just 0 dB or 1. It becomes 1.76 dB, corresponds to 1.5. So it has a directivity. Even though it's not so obvious, but yeah, it has directivity. And from the antenna directivity, what we want to get is the antenna gain, all right? So for the antenna gain, it's related to the first thing we need to consider is we have several parameters. The first parameter is, because we said that our antenna at the transmitter side is usually faded by the transmitter, right? So we have a transmitted power. This is the transmitted power or transmitter power. Usually, if the efficiency is not very high, or if the efficiency is not 100% or perfectly, that means this power is not the power radiated from the antenna, because we have another parameter. This is the radiated power. From the antenna. So then there should be a difference, right? So the transmitted power from the transmitter, and the radiated power from the antenna, there should be a difference, right? So this difference define it as loss. So this is the loss between the transmitter and the antenna. That is power loss. Here it is from the transmitter to the antenna, the dissipated light, dissipated power, as heat, alright, as heat. So this is, so for the antenna designs, what we want to do is just reduce this part, right, to increase the, or to improve the efficiency of the antenna. So the parametric size, the radiation efficiency, is defined as a parametric size defined by the radiated power divided by the transmitted power. So previously, when we analyzed the peak directivity, we just consider it as the radiated power, right? The maximum power at the peak point divided by the radiated power. This is the directivity, the peak directivity. But however, here we want to get the gain of the antennas. It can also be defined by the peak power at one direction divided by the transmitted power, not the radiated power. Okay, so just take care. That's why there is really, or strictly, there is difference between the antenna gain and the antenna directivity. So that means because the VT can be defined as, also can be expressed as the radiated power can be expressed as psi, the efficiency times the transmitted power, right? So that means this part can be expressed as RAD divided by psi 4 pi r square s, the density, the maximum power density, it equals psi times 4 pi r square s max divided by the AD, right? So it is expressed as psi times directivity. So that means that antenna gain equals the radiation efficiency times the radiation efficiency times the peak directivity of the antenna. And why? Commonly, when we really regarded the directivity as the antenna gain, or regarded as the antenna gain as the directivity, that's because for mostly the antennas are designed that it has perfect matching, and the H is due to the ohmic loss, or the ohmic loss. Due to the ohmic loss, the ohmic loss can be neglected. So, for example, we really just take the antenna as a lossless antenna. Then the radiation efficiency can be 1. and then again, of course, the directivity. So that's why we just based on our measurement on the directivity, and we can get the gain of the antenna. So now we introduced the parameter about the radiation efficiency, right? So it's related to the ohmic loss of the antenna. So we're gonna take further introductions from this part. The radiation efficiency. So for an ohmic loss, we need a course for the antenna. It has transmission line, right? Faded onto the antenna, right? Like this one, and there should be what? Here is the transmitter here. So there should be a connection between both sides, right? So first, let's just consider the antenna is regarded as a load. So we take the antenna as a load. So we use theta to express it. It has a resistive part or component R and a reactive component X. So for the resistor or the resistive component, it's gonna consume the average power, the average radiated power, right? So if we assume that there's current anode flowing inside of it, and this is AC current also. So the average value is I know, right? So the transmitted power can be expressed as half I know square R. All right. So that means if we take this part, you can see it has a resistive component and also has a reactive component. So as we radiated, the transmitted power can then be separated to two parts, right? First part is radiated, and another part is lost due to the ohmic losses. So that means this resistor, the resistor can be as two parts. First part is used for radiation, another part relates to the ohmic losses, like this one. So that means this part must be taken into two parts again. The radiation for that one and the losses, ohmic losses for that part. So the radiation efficiency side is defined by the radiated power divided by the transmitted power. So, all right, it comes as the radiated power divided by the radiated power times the lost power, the ohmic loss, and so it can be defined by 1 plus D divided by loss. All right. So if we wanted to increase the efficiency, try to reduce ohmic loss this is the radiation efficiency, which relates to these two parts together. Sorry, I think I took one calculation minus plus this part. So it's really smaller than that, all right? So the perfect condition that is important. And we really use maybe for the materials. On the surface of the materials, we need to poach some materials with high conductivity to reduce the ohmic loss. And we also wanted to had to keep the surface as much smoother, all right? It's much more smooth, and make sure that it just used it to reduce the ohmic losses. So the next is for any antennas, especially for the Hawaii antennas or for the dish antennas, it should have aperture, right? Antenna aperture. The antenna aperture usually affects the beam pattern and also the antenna gain and the directivity also. So for the Hawaii, take Hawaii antenna as an example. First is the effective antenna, and the effective antenna, or the effective antenna aperture. So let's come back to this part, because from the load to the antenna, there is a connection part here, right? So this area is really regarded as the effective antenna aperture, and it can be defined as the instant power divided by the instant power energy, the power intensity. So the intersected power or the instant power are also the same thing. We just here we take it as a antenna at the receiver side. All right. So this is the here forwarded to here and to here the detected by the detector here or the receiver, like this one. So for this part, it includes what? It includes the receive antenna's aperture, the physical aperture also, and the receiving cross section together. And so this is the effective antenna aperture, and we also have physical antenna aperture. The physical antenna aperture is like this one, right? The horn, the front of the horn. This is the physical. We use EP to express it. So now, if we take the solid angles or the pattern solid angle, so pattern solid angle is omega p, all right? So it can be, if one related to the effective aperture, it can be expressed as this one. This is a solid pattern angle, and also the directivity can also relate to the effective aperture, because default 4 pi over omega, all right? So it becomes 4 pi over lambda square times A. So I think Most of you should be familiar with this equation. Of course, we want to get the directivity antenna gain of a whole antenna, for example, and we know its effective aperture, and we know the frequency of the wavelength it operates, then we get the directivity, alright? And further, we can get the antenna gain. So this is the, but what's the difference between the physical antenna and the effective antenna? There is also an efficiency here. So like the antenna gain and this directivity, right? There is efficiency like this one, and there is also an efficiency, and we call this efficiency as the aperture efficiency. Aperture efficiency, and but this equation would not work for all kinds of the antennas, because, for example, for the loop antennas, for the Hertzian antennas, it's difficult for you. You cannot define the aperture, the physical aperture, right? So there is no such expressions for such kind. But for the whole and the dish antennas, we use such equations. You can just measure the physical aperture and then get what the an effective aperture, and then conduct that to get the directivity. And if you know the efficiency, and you can get the antenna gain also. So you can just calculate these values of these equations, and do not need to get the values from the producers. So after that, we know the antennas, the parameters for the antennas, right? The width or dimensions, and the antennas for the directivity, and the gain, and the antenna aperture also. So then if it's just for one antenna, right? So if we have two antennas, the first, take a whole antenna as an example. First antenna, and we have another this direction, another antenna, and so for this antenna, as the transmitted power is this one, and the received power is this one also, and the radiated power here, and the intercepted power. And we also assume that the main direction or directivity, the peak directivity, the direction for the peak directivity is also along that at the receiver side for the reciprocity, right? So what we wanted to do is we wanted to get the a formula which can connect both sides together. How to do that? Is the phrase transmission formula. So the phase transmission formula connects the antennas at transmitter side and receiver side, also the propagation between both, right? So just for the simplest format, there is no other medium, it's just a free space, in free space. And we also assume that the distance between both antennas, R, satisfies the far field. It's in the far field region. So now, if we want to get the For example, firstly, we just assume that our antenna are isotropic antennas. For isotropic antenna, the power density can be expressed as the transmitted power divided by 4 pi r squared, right? For the isotropic antenna. But for the whole antenna, we know that its power density, received power density equals the isotropic power density times the gain, alright? It's related to the isotropic antenna. So the gain of the for the transmitted side, actually, why? Because now we just consider transmitted power, and we assume that our received power density, we do not consider the antenna at the receiver side now. So it becomes the efficiency of the transmitter and times the directivity, the transmitter times the power density of the isotropic side, right? So it becomes as ST dt, this equation, times transmitted power divided by 4 pi r squared, right? So for the directivity et, so we want to relate it to the antenna aperture. It equals 4 pi or lambda squared times the antenna aperture, right? So it can be further expressed as T et divided by lambda square r square, right? So now we take the receiver in consideration. So the intercepted power from the antenna at the receiver side, it equals the received power density times the area, alright? So the area of the receiver in R, or the aperture, also is also regarded as the aperture of H. So it becomes psi g et AR et divided by lambda square r square, right? So this one, and also there is another parameter we need to consider as the for the receiver side. The received power equals the intercepted power times the receiving for the receiving antenna. There is also another efficiency, right? So it becomes psi t psi r at r pt divided by lambda square r square. So this is the expression for this one. And then when we come back to the expressions of the antenna gains, it is expressed because for the antennas, actually sometimes maybe it's difficult for us to obtain the efficiency and the aperture, but when we come back to the expressions of the gain of the antennas, it can be expressed as this one, for example. So gain equals cosine times directivity. Directivity is 4 pi lambda square times e, right? So this equation. And if for the whole antennas or the dish antennas, the eta, the aperture efficiency can be neglected or it's perfect antenna, so it can be as the physical lecture. And beside can be further simplified as T r times lambda over 4 pi r squared. So now I think you should. Okay, I lost one reference T. So that means the received power divided by the transmitted power equals dt dr times lambda over 4 pi r squared. So I think this is the commonly used phrase formula, alright, for the calculations. And here we take the GTGR. Generally, is because the beam pattern is axis dependence, right? Depends on the in the Cartesian coordinate system, depends on r, theta, also y, right? And GR, also the same thing. Theta, phi, right? So that's why here we just consider as along the same the main line of the for the peak directivity along this line, and we call this line as the line of sight. All right. This is just for line of sight. You consider this part. If, for example, the antenna at the receiver side is along this direction, for example, right? So there should also be some energy and received or intercepted by the antenna at the receiver side. And here we need to consider in the Cartesian coordinate system, we need to consider the angle, the radial, and the azimuth angle also, and take the calculations on that to get the exact values for the gains, antenna gains for these directions, right? Because they are not along the main directivity or direction of that. So now we also, if for example, if our antennas, the gain of our antennas equals 1, so it means if there is isotropic antennas. For isotropic antenna, that means GT equals GR equals 1, right? So that means this equation, come to here. A received power divided by the transmitted power equals lambda over 4 pi r squared. All right, and we define it as 1 over LFS. So LFS means the free space. Now this is the loss, right? The received power divided by the transmitted power. For the antenna gain equals 1, and there is only the loss due to the propagation, right, from this side to this side. So we call it a free space path loss. So we can see that if you find the equations of that one is already defined by 4 pi r divided by lambda square, right? The free space path loss. And it's related to the distance between the transmitter and the receiver, r, and also inversely proportional to the square of the wavelength. So this is the free space path loss calculation. How to make just from this equation here, and the condition that the antenna gains for the transmitter and for the receiver are equals to 1 here. So this is for a line of sight propagation. And how about if there is a surface here, and we have antenna at this one, and antenna at this side, right? So it related to here, and then reflected by the surface to here. And we can also express that by this equation. But here now it can be calculated to a new form here. So we're gonna introduce this part next week. Okay. Now I think we are done for this week's course, and we're gonna see you next week, Monday next week. 好，那我们下课。今天的这种一般都是查出来它的那个口径的效果，然后或者是有可能每个100个天线的话，人家厂家直接告诉直接告诉。
是不是前几次都讲的是电子对，现在开始讲这个跟天线科技相关。
啊，对，这样后面我再继续讲。
然后呢，周四他会去那边观察。
明天周四我上午是下午可能也有上午找个时间。周四应该都在，因为这2天周末校友来校所以他们在那布置那个暗室的事情。行，谢谢。
Professor, you wrote here about this equation. So how it become minus like it was first plus and then you wrote it?
Oh, I read this wrong. It's really lost.